Hello and welcome to this new chapter. So here we'll be exploring graphs of exponential functions. It's important that you understand why they behave the way they do. So what happens here right from the start at this looking at this graph here, we've got all the intercepts of those graphs is going through point 1 here. This value is y value is 1. So why do they all share the same intercept? It's because first of all there is nothing added here after this function here, and the base of the function, okay, is a natural number, is a positive number, and it's raised to the power of x. Okay, so x's are now in the exponent, hence the name exponential functions. All right, so why is that they have intercept of 1? So any any value raised to the power of 0, where x here on the y-axis is 0, will give you 1. That's why 2 to the power of 0 is 1, 3 to the power of 0 is 1, and so on. Any value. A million to the power of 0 is 1. Okay, so no matter what the base is, we calling this number 1.5 the base of this exponential function. Okay, so then what you notice from the shape of these graphs is also that the larger the base, the faster it will rise. Okay, so it's needless to say that 5 to the power of x would grow faster than all of these curves. Alright, so what if the base was negative? Can we have a negative base? No. Here we have here negative, the power is negative. So will never be negative number, because if a negative number raised to a positive power will be positive, and then negative number raised to, it wouldn't have an exponential graph. Okay, can happen is that x can be a negative value. On this left side of the graph, you see all of these graphs will have an asymptote, a horizontal asymptote of y equals to 0. Horizontal asymptote on the left. Okay, why is that? Because really what we're saying is that what is 3 to the power of minus 3, or minus this, or this means that 1 over 3 to the power 3. What if then we substitute x to be 100, a negative 100? It will be 3 to the power of negative 100. What is that? This is 1 over 3 to the power of 100. So that's a huge number in the denominator, and 1 divided by a huge number is an extremely small number. That's why it's almost 0. It's not exactly 0, but it's very close to 0. We're saying that this is close to 0, it's not 0. Okay, so that's why the further to the left you go, asymptote will be closer and closer to the x-axis. All right, so no matter what the base is, as long as it's positive and we're raising it to a negative power, it will become very close to 0, but not negative. There is no power that can turn this 3 to the power x will never go under the x-axis. Notice that as well. Now, there are different graph transformations that we can apply. We can multiply it by a constant scale factor here, and it will raise, it will make if a is positive here, it will, and above 1 raise the gradient. It will shift, it will make it steeper. Now if a is negative, we'll look into graph transformations in a couple of videos from here, but for now all that matters is that you understand the basic functionality of exponentials. So here is just to show you the difference between a geometric and arithmetic function here. So arithmetic series here is just a constant added together. So and a geometric or rather exponential is what I've just put on the graph here for you. These, if you plot these values there, the blue line is 1, 5, 9, and so on, uh, set against the x value, where n there is just like the index of the number of its position. So we're saying that here n is 1, here n for 2, and so on. So 2 is, and so on. So for exponential, you might be wondering where do I get these numbers actually. So this is just 2 to the power of 0, this is 2 to the power of 1, this is 2 to the power minus 1, this is 2 to the power minus 2, and this is 2 to the power minus 3. So I plotted, I'm saying I'm plotting 2 to the power x, so I'm substituting minus 3, minus 2, and so on. So this is 2 to the power of 5, and so on. So you will get, you will see that when we are at 2 to the power 0 is at 1, and anything to the left of x values, when x values turn to negative, then the number gets closer and closer to the x-axis. I tried to show that to you on the previous page as well. And so what we are saying here is the common ratio is 2. You understand common ratios when we study geometric series in year 13 rather, but here's just the heads up for you. You don't have to know anything about geometric series, but just understand that there this 2 is multiplied by itself as we go further to the right of the graph. Okay, so what's the next few terms of this part C, this series? What do you think? What's happening here? If we have one, what's happening here? What's happened? What do you think? Is this arithmetic series? This was arithmetic series have a constant difference, whereas the adding or subtracting of some constant value here's multiplying. Okay, each term is multiplied by 2. Is multiplied by the base itself. Here, 1/2 you could say is multiplied by 2, and so on as we move forward to the right. So here is multiplied by a ratio of 0.8 actually. Okay, so we could say the base is 0.8 raised to the power of x. Then this is where x is 1, and so on. So here's where x is 1, here's where x is minus 2. 0.8 raised to the power minus 2 actually makes it bigger. Okay, so yeah, we'll explore that later. So you just need to have a guess what's happening. This is just preliminary test here. This is multiplied by 3 over 2. This is multiplied by 3 over 2. Okay, so what's to learn about this yellow graph here? What do you think if I plotted it here? If I had the uh, this red line reflected in y-axis, what would be the what would be the exact value? Let's say this is 2 to the power of x. So what is it? What is its reflection in y-axis? What do you think the function would be there? I'm saying this is f of x here. So what's the function for its reflection exactly? If I drew it perfectly well, it would appear as this other red line here, right? So what do you think is that? Well, it would be actually uh, how do we transform a graph in y-axis? The x value is split, so it will be 2 to the power minus x. All right, the function of this graph here, it is just simply flipping the values of x. All right. Now, what does that minus do? That you could say, I could break that up into 2 times minus 1 times x, right? What is 2 to the power minus 1? It's going to be a half raised to the power of x. So I'm saying these two are equivalent. If you see a negative power in an exponential, you can rewrite it as a positive power. If you have a function such that f of x is, let's say, 5 raised to the power minus x, that's the same as 1/5 raised to the power of positive x. Why? Because I separated the power as minus 1 times x, and I rewrote 5 to the power minus 1 here. Alright, so therefore, if you see exponential decay graphs like so, uh, they have a base that is less than 1. So here's the point to learn. If our base here is less than 1 here, base its value, when we put 1 over it, it turns into less than 1. Is less than 1, it's it has a graph that is portraying a decaying function. It has a negative gradient. Okay, so let's look at it one more time. I talked about these questions. It's asking what does these curves have in common? They all have a common asymptote. They pass through the intercept of 0, 1, and the asymptote, why is the asymptote y equal to 0? I tried to explain that in a earlier. So how can we rewrite a to the power of minus x? We can separate the power of as minus 1 times x, so that is basically 1 over a to the power of x. All right, so that's what I wrote here. That's what is the limit of this now. If x is approaching a large value here, well, 1 over equal, these two are the same. 1 to the power of ax equals to 1 over a raised to the power of x, because 1 to any power doesn't change 1 anyway on top of the fraction. So these two are the same. So what I was trying to say is that if a is a positive number and is bigger than, if a is already bigger than 1, let's say a is bigger than 1, then 1 over a will be less than 1. Okay, therefore 1 over a will be the opposite. 1 over a will be less than 1, therefore we will have this shape of the graph. It will come from uh, very positive values on the negative side. It will be just reflection of these graphs on the left side. Alright, so let's explore what's in the next slide. So here we are just going to look at x to the power x and half to the power x. So if I plot the 2 to the power of x, I'll substitute these values on the table here, and we get in the y values. So I already shown you that graph. So, and here's these two graphs. So 2 to the power of x is the reflection of half to the power of x in the y-axis. Alright, I tried to explain that to you. And you could have a blue curve, its reflection is obviously going to be 2 to the power of x. Okay? So, and if you have a negative in front of the function, that would just reflect it downwards. Okay, so in this holds you understanding a lot of graph transformations. So make sure you review what we learned in chapters 4, where we went through all these graph transformations. Okay, so sketch these graphs. So if we had to sketch 3 to the power of x and so on, we would be sketching. It would be very similar to 2 to the power of x up to where it's negative. It might be a little below that, but here it will be above it. So this would be y to the power y equals to 3 to the power x and so on, and 1/3 y equals to 1/3 to the power of x would be reflection of that there. So I'm not drawing accurate graphs here. I'm just saying roughly what the shape would be. Okay, so now here is a quick reminder about percentage changes, because in the next example I'm going through some changes. This is from my year 10. I apologize if it's too preliminary, too basic for you. What do you do when you increase a price by 20%? Let's say its original price, the shoes were £40. Now, what happens when you increase it? So, this is what you would do. You say, what's the 20% as a decimal number? I need to add that uh, as a uh, as a multiplier. We could factorize the 40 out, and we say that just think 1 plus 0.2 multiplied by 40 is the multiplier, and therefore we add to 1 to get the multiplier. Remember that? So what if you have a percentage decrease? In the next example, a car average value falls 15%. So because we have a fall, this is a percentage decrease after 1 year. You say that base, it was £10,000, so we multiply it by 0.15. If we factorize the 10,000 out of that, that's why the multiplier is 0.85. Okay, you would just take 10,000 and multiply the 0.85. So that's just making sure you know what's percentage, because in the next example we have some percentage calculations. Now, this is not from your book, you don't have this example in your book, but it's very, very good to understand what's happening and what it's asking us about. So a bacterial population, a bacterial colony grows by X%. We don't know the percentage growth, percentage growth per day, all right? So it had a population of 1.2 million at the end of the third day, and it had a population grew to 1.5 million at the end of the sixth day. So from the third day, you could say when time is 3, it has 1.2 million. When time is 6, it has 1.5 million population. What is the daily growth rate as a percentage? Right, so think, what do we do? Alright, so you're familiar with compound percentage changes, right? So this multiplier, I tried to show you those multipliers because this is the multiplier, but we have third day. So whatever the initial population was, we say A was the initial population, initial value. On the third day, we have we have it multiplied. This r is our 1 point x. We don't know what that percentage is. 1 point x, that is raised to the power 3. All right, on the third day, and on the sixth day, that it will have r to the power of 6. We will have multiplied by the same. We are assuming, if it's not clear, we're assuming the same percentage the same percentage of change. It's uh, maybe it's not realistic assumption, but for this purpose, for this question, we're just assuming that percentage doesn't change. It's the same 1 point x that we are multiplying across each and every day. All right. So, what can you do to solve this kind of problem? You cannot just add or subtract these two fractions, can you? I explained 1 plus x makes I'm writing as 1 point x, as x being a decimal number, all right, having turned this percentage into decimal number. Maybe I should write 1 plus x over 100. That makes more sense for you, right? So uh, that's what we do, all right? So what you do is say, I don't know that initial value. A is our initial value at time 0, okay? Initial. Then this is just writing 1.2 million uh, in shorthand, scientific notation, and this is writing 1.5 million in scientific notation, right? So these two equations, I want to solve them for x, but what you notice is that I can't just add or subtract them. If adding and subtracting them doesn't help me to solve for x, what can I do? I can divide one by the other. The bigger one is the second one. So to solve this kind of equations where you have only change in exponent and here's multiplication, you can divide one by the other. What happens is when you divide one by the second one, divide by the first one, the a's will cancel away. That's nice. Alright. And then we'll have 6 minus 3. And remember the index flows there. On the left, you're subtracting the indices. On the right, you can just say that the 10 to the power 6 is cancelled away. So there was 10 to the power 6 there, 10 to the power 6 there. That cancelled away. And so we left with this ratio. So it's simplified like so. You can say now this is just 1 plus x raised to the power 3, right? Which equals to this number here. What's 15 over 12? Doesn't matter. 15 over 12 can be written as 5 over 4 or 1.25. Alright? So to solve this equation, we raise both sides to the power of 1/3, right? You say this, I want to get, or cube rooting it. In other words, when you're raising something to the power of 1/3, you're cube rooting both sides. Alright, so 1 plus x would be cube root of 1.225. That's what we do. Alright, let me write this off. So then we end up with this number here. So what's x? Take away 1 from both sides, 0.772. Now this is a decimal number for the percentage, so the percentage will be 7.7 actually per day. Alright, so assuming that the percentage didn't change across days, we assuming that it was a constant percentage change every day, which is somewhat maybe it is realistic. Okay, so what part B is saying, what's the initial number of bacteria to the nearest 10,000? So you have to work backwards now to find the value of A. Okay, capital A here. So you substitute this into either of those equations. We're going to take the first equation, substitute it back into that, and work it out. So divide both sides by what we have here. We get A equals to actually 0.96 times a million. Alright, so to the nearest 10,000 it would be 960,000. Alright, so that was the initial population. Alright, let's say somebody sneezed and that many bacteria fell on certain. That's fine. Alright, so part C is saying how many bacteria will be there at the end of the 10th day. Alright, so given the same daily percentage growth continued for every day in between. Alright, so there is an assumption that you can explicitly you can take. So you just basically assuming the same formula, A is this value here, all you have to do is say value of the index is going to be 10. Do you understand? So the index changes rather than anything else in this exponential model. It's a exponential model after all. Okay, so you will get 2 million, just over 2 million as the answer. All right, you can test it, put it in your calculator, and you should get the same answer. Okay, so good luck practicing these values. These questions 6 and 7 are rather uh, well, just have a go at it. And if you want some help, I can reveal the answers here, and so on and so forth. So I hope that was helpful. I'll see you in the next video.